Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I think let's start the talk. It's a great pleasure for me to welcome Yi to give a talk at Microsoft Research. Yi obtained his bachelor and master degree in 1995 and 1997 and 1999, both from Tsinghua University. And he obtained his PhD in 2005 from University of Illinois, Urbana-Champaign. And since then, he became a junior faculty member at Vanderbilt University. His research interests include overlay network, peer-to-peer systems, multimedia systems, and wireless sensor networks. Yi will give a talk on multimedia streaming in self-organized mesh networks today. And without further ado, let's welcome Yi for his talk.
So thank you very much, Gene, for the nice introduction. So let me tell you a little bit first about the places I have been in the past few years. So I spent many years in Illinois getting my PhD degree. And in the middle of that, I spent the most amazing summer in Microsoft Research doing my intern. So then I returned to Illinois to get my degree. After that, I started my new career here at Vanderbilt University. So now I'm coming back to Microsoft Research for a short visit. So it's so nice to see lots of old friends here. So I have updated the title of my talk a little bit because I want to give a more focused talk. In the past few years, I've been focused on the overlay multicast, and this research will continue to be the main component of my research portfolio. So this will be main theme of my talk. But first, let me say a few things about my overall research agenda. So my general research interest is to provide advanced networking service to a new set of multimedia applications. So what you see here is that at the network layer, you see that the internet is becoming more ubiquitous and heterogeneous, incorporating different types of wireline and wireless technologies, such as the wireless mesh and the home wireless network. And at the application domain, you see a rich set, but still growing sets of applications like peer-to-peer file sharing, media distribution, and the mobile multimedia service delivery. So the traditional internet gives a very narrow and very limited set of services supporting these applications like connectivity, like routing and flow control, traffic engineering. So these services are too limited to support all these applications. So my goal is to design a new set of networking services to support these applications. And these components will compose themselves into a new enabling service platform or service layer, whatever you would like to call it, to support these new applications. Now, the focus of my talk today will be the middle column here. So it will be, I will present my past work on the overlay networking service to support the multimedia distribution application on top of the internet. So that's the main theme of my talk today. So multimedia distribution. There are lots of applications here, but the basic semantics they share in common is that you want to distribute a large volume content from the source to multiple receivers. Now, this is the context of my talk. I will focus on the scenario of one piece of content, a single source, and many receivers. These receivers may want the content, they want the same content, but they may want the same content over different times. But that's the basic scenario, one piece of content, a single source. Now, you can do the distribution in the unicast way, you can do the distribution in the multicast way. So the problem of unicast is that you have to, sometimes the same packet will be replicated over the same link multiple times, which can easily congest the link some bottleneck link most likely to happen at the server side. So that's the problem of unicast. Multicast solved this problem, but the problem of multicast is the management of the membership. So a router here can easily handle thousands of multicast sessions, and for each packet going through this router, the router has to determine which session this packet belongs to, and depending on the membership, how do I replicate the packet and which direction this packet have to go. So the state management is a big overhead in the domain of IP multicast, which brings us to overlay multicast. So the idea of overlay multicast is that you still utilize the unicast, but here you ask the receiver to share the duty of relaying the content, which used to be the duty of the sender. So the notion of overlay is that underneath, at the networking layer, you see a bunch of unicast connections, but if you put an overlay layer here, you see a very clear tree structure, which represents the content relaying a relationship. So that's how you get a notion of overlay multicast. Now, overlay multicast reaches a very perfect trade-off between the IP multicast and the unicast, actually. So in terms of deployability, overlay multicast is a perfectly deployable solution on the existing infrastructure. But in terms of the scalability for the server load and the efficiency at the networking cost, overlay multicast is not as good as IP multicast because the packet replication problem still exists in the domain of overlay multicast. So I give an A- to the overlay multicast. But overall, this is also proved by the existing research. The overlay multicast is a very good solution to address the content distribution problem. So that's the current research landscape. Okay. So what I'm interested is how the overlay multicast is going to perform to meet some of the meet challenges from the application perspective. So here I picked two challenges. The on-demand challenge, by on-demand challenge, I mean two things. First, the receivers may want to retrieve the content at different times based on their personal demand. Second, the user can choose to freely join or leave the session anytime they want. This is the on-demand challenge. Throughput challenge comes from the insatiable demand posed by the end receivers. So when it comes to multimedia distribution or streaming, so the bandwidth requirement of the user just always want to have a higher bandwidth to receive higher quality video stream. So they can't get enough of that. So let's see how IP multicast performs with these regards. So for the on-demand challenge, the IP multicast, the content is always pushed from the source to all these receivers at the same time. So IP multicast doesn't do a good job meeting the challenges here. For the throughput challenge, and you see that the maximum achievable throughput in the case of IP multicast is actually bounded by the capacity of the bottleneck link, the capacity of the thinnest link in the whole tree. So, the support of IP multicast to the throughput challenge is quite limited. So the question here is that how the overlay multicast is going to perform, regarding these challenges. That's what I'm about to find out. So the question we ask ourselves is that, are there any features only unique to overlay multicast which can help us address these challenges? So the first feature is that you see that there are a diversified set of abundant resources available at the end host at each end host in overlay multicast, such as the CPU cycles, the storage capacity, and access bandwidth. The second feature is that overlay multicast allows you to enforce very flexible network management. This is not available in the context of IP multicast. So if you're familiar with the DVMRP and IGMP protocols in the IP multicast domain, see, you really don't have too much freedom choosing who your parent should be, how many trees you can build, things like that. So the problem is, can we utilize these features to address the problem that I have raised in the previous slide. And then how do we utilize these features to design effective solutions, effective overlay multicast solutions? So this is this picture. This picture basically this is the overview of my talk. I will present three pieces of my work, and you can see that this picture actually tracks my research thinking along a time range of a number of years. So what I did is this: I first focused on the on-demand challenge. Okay, then I developed the first work. So the basic idea is that you can utilize the end host storage space to support the on-demand delivery of the content of the multimedia content. And we have developed a temporal dependency model and a asynchronous distribution solution. And the key thing we have learned in this piece of work is that with only very small, if each end host only contribute a small portion of their storage space to catch the content, not necessarily the whole content, but only a small portion of the content, you can dramatically increase the scalability and efficiency of your solution. So then I focus on the second challenge, which is the throughput. How do we maximize the throughput to the end users? The key idea here is that is also very straightforward. You just split your content into multiple slices and set them off in parallel to multiple trees. So we explore the wide diversity of overlay networks. And in this work, we have developed, we apply the multi-commodity flow model into the overlay network domain, and we find that the model fits the scenario very well. And on top of this model, we developed the primordial algorithm for the multiple overlay tree construction. So there are some interesting results in this domain. Okay, these are the first two pieces of work we have done. And this is the last work we have done. So what we do here is we combine the wisdom and the lessons we have learned in the previous research here, and we propose a solution that addresses both challenges at the same time. Because it always happens that the users in application can have both requirements. They want to have they want the overlay multicast to give them the high bandwidth throughput, but meanwhile they want to have the freedom to join or leave the session anytime they want. So the last piece of the work will be the joint solution, which combining the techniques we have developed in these two pieces of work. So that's the overall picture of the whole talk. The roadmap is this. I will first talk about the work I will first talk about the overlay-based on-demand media distribution, which is the work that utilizes the end host storage space to address the on-demand challenge. The second piece of work will be the one that try to maximize the throughput in overlay multicast. The final piece of the work will be the work that propose the joint solution. Okay, that address both challenges. And this is the line of the first piece of work. I will first talk about the basic idea. Then I will talk about the concept of overlay graph and how do we do the tree construction algorithm. And I want to talk more about the performance evaluation. So this is the problem. On-demand distribution means that in the context of this work is that you have a single source here. These are the receivers. These receivers want the same content, but they want the content at different times. That's the first challenge. Second is that they want different portion of the content at different times. So what I mean is that when you watch a DVD or VCR, sometimes you want to go back and forth. You don't want to stick with the original schedule of the program. You have the freedom to jump ahead to see the content ahead of the time. So these are the two challenges here. So our goal is that we want to build a solution that can meet these user requests. At the same time, we want to minimize the system cost in terms of the server load and the network bandwidth consumption in the middle. Now, the basic idea of the solution is to use the caching space at the end host. So suppose I am the read client, so I am the first one to request the content from the server. This is the server. So the server will give the first copy of the content to me. So what I do here is that after the playback of a certain frame of a certain video frame, instead of drop the frame immediately, I will choose to cache that frame in my local buffer for a certain amount of times, let's say 10 minutes. And 10 minutes later, I will drop that frame. Okay, I will do the same for the next frame, the next frame. So you can imagine that there is a circular buffer going on along the playback, going along the time axis of the playback. Now, let's see the second client, the yellow client comes, let's say 5 minutes later after the first one. So if I'm the yellow client here, so instead of getting the content from the server, I can actually retrieve it from the buffer maintained by the red client. So if I do that, I will offload the server. So that's the whole idea. So the key word here is content reusing. By reusing the content cached at the client side, you can actually offload the server. That's the whole idea. And likewise, if the yellow client comes, let's say several minutes after the the green client comes several minutes after the yellow client, and also the yellow client will also do the same type of buffering. Probably the green client can reuse the content from the yellow client. So you see here a content reusing relaying relationship going on here. Yes.
In the sense of just the application domain, how many clients are you targeting? How popular is the content?
How popular is the content? So when we design this piece of work, we are thinking about popular video release, hot video release, which can possibly serve hundreds or thousands of clients at the same time. But these clients may want the content over, at different times, over the range of hours. That's the basic scale we're considering when we design the solution. Okay, so if we summarize this content reusing relationship, we can actually draw overlay graph here. So let's say the directed edge going from one client to the other means that, for instance, in this edge, which means that the yellow client can reuse the content of the red client. So that's what it means in the overlay graph model. And the weight of each edge will be the distance between these two endhosts. And you have different ways to measure the distance between two endhosts. It could be a hop count, it could be a delay, end-to-end delay between these two endhosts. So this is the idea of the overlay graph. And with overlay graph, the problem of finding a distribution solution will boil down to find a spanning tree on top of this overlay graph. Okay, so that's the basic the basic line of the method. You can if you have more you have other goal, you can also tune the constraint, either the constraint or the objective of your formulation to achieve different goals. For instance, if you want to minimize the network bandwidth consumption in the middle, then the question becomes to find a minimum spanning tree, okay, on top of this graph. If you want to reduce the server load, if you want to bound the server load, then your question becomes to find a minimum spanning tree whose outbound degree from the server is bounded. Okay, so that's you can go on and on, by tuning the constraints, either the constraint or the objective of your formulation, to achieve different goals. So that's the basic algorithm. And the challenge here is that how do we design a distributed solution, okay, to achieve these goals? And our goal is the following. When we build a tree, we want to build a tree in an incremental fashion, which means that the node will come and join and leave constantly. And we don't want every time such things happen, when a node or join or leave, we don't want to reorganize the whole tree. That will be too much overhead, and that will also cause too much interruption to the existing nodes. So we don't want to change the tree too much. Also, we want to maintain the tree in a dynamic fashion. And the last thing is that we want to make sure that the decision to build the tree is made by each individual receiver. Yes.
So how is the tree related to the content?
How is the tree related to the content? Again, in this piece of work, my assumption is this: one source, one single content. Okay. With regard this source and content, the overlay graph is built here. So, for instance, if the source is now broadcasting the movie 24, the overlay graph is also built regarding this title 24. Okay. And what you want to do is to build a tree on top of the overlay graph.
Okay, but they're all accessing it at different times, and they skip over pieces and all that stuff. So is that reflected in the tree?
Yes, which will be. I will talk about how the tree is dynamically maintained. The tree keeps changing over time. Oh. So let's say we have a tree here. These are the existing receivers, okay, getting the content. If a new guy joins, so what will happen is that the new receiver will find who are my predecessors. The predecessors are the existing receivers who have the content that I need, okay? Then I will find the closest predecessor as my parent and connect to the parent. So that's the procedure if a new node joins the tree. So there might be two questions probably you will have, in this algorithm. First, how do you know who has what I want? How do you know who are my predecessor in this tree? That relates to the content published and subscribed service. So we need some type of publish and subscribe service to basically update with who has the content that we want. So there are a bunch of solutions we can leverage. Okay, we can have the easiest one will be a centralized solution. So let's say we let we use the server to do the bookkeeping job. Okay, so every time a node joins, the node will notify the server which is the content that I have. Okay, and also each time a new node joins the multicast, the node will ask the server, who are my predecessors. This is the easiest solution. Again, then finding the closest predecessor. This is the measurement job that is up to the end host. It's up to you to measure, how distant you are from the other receivers in the multicast. So that's the algorithm for that's how you adjust your tree basically when a new node joins. Let's say a node leaves. Let's say I am the one living here. So what I will do is that I will tell my children, I am leaving. Find yourself a new parent. And the affected children will basically reattach themselves to the tree using the algorithm here. Okay. So a question you might have here is that will cause interruption, right? I am leaving, I affect my child. Okay, my child is out the streaming, because my child has to reattach themselves to the tree, probably the playback at these nodes will be affected. That is possible, but here the buffering will come to the rescue because I say here that the children will get the content from the buffer of their parents. So when their parents are leaving, so what happens is that if I'm the parent here, I will notify my children that you want to find yourself a new parent right now. But at the same time, I still have some remaining content, in my buffer. So when I do that, when I tell my children to reconnect themselves to the tree, at the same time, I will continue to push the remaining content to my children. So I earn my children some buffer time to do the reconnection. So if they succeed to reconnect to the tree within the time limit that the content in my buffer is drained, okay, they won't experience any interruption. So that's a good thing about content buffering. Okay, so that's the basic idea of how you deal with a node leaving the tree. So this part is actually more interesting. So performance evaluation, I choose to evaluate the server load and the network bandwidth consumption. And I choose to perform closed form analysis and NS2 simulation. When I do the analysis, I choose two types of access modes. The first access mode is called sequential access. I also call it theater mode. So what happened here is that if you're a client, you will always watch the movie from beginning to the end. You will stick to it, like the way you watch a movie, okay, in a theater. The second mode is what I call the random access mode. It's like you watch a VCR. You can choose to review different portions of the movie at any time you want. These are the two types of modes that I chose when I analyze the performance of our solution. So this is the methodology. I see the whole movie, the whole content, as a linear sequence of many, many small units. Okay, and then look at one of the units here. Let's say very, very small unit. Let's say 1 byte. Okay. And I see that how this 1 byte is served by the server. Now, let's see these are the clients line up, okay, in the time axis. These are the clients requesting this particular byte of data along the time. So the first client will definitely get the get the content from the server. Now, the second receiver probably will reuse the content from the first receiver, and so on and so forth. But they can happen that if these two adjacent receivers, neighboring receivers, are too far away from each other, along the time, it means that you cannot reuse the content of the previous receivers. In this case, you need to issue a request from the server, and the server will give you another copy. Now, if we denote the time difference, from here to here, from the first time that the server serves this content, and the second time the server serves the content again, if we denote this time difference as tau, and if we can derive a closed form of expected value of tau, okay, then this form 1 over expected value of tau will be the expected server load with respect to this particular piece of content. Now, if I perform integral over all contents in the entire movie, I will get the server load, average server load. Now, this is how the curves look like. The blue curve is the curves refers to IP multicast. So you see here, IP multicast, the server load to the IP multicast keeps increasing. This keeps increasing when the request rate grows. Okay, and the red lines are the performance of overlay multicast, and you see that the curve of overlay multicast is actually capped. So what happened here is this. Before this threshold, when the request rate grows from 0, increases from 0. So what happened is that at this moment, the requests, the average inter-arrival time of neighboring requests are still far away from each other, such that they cannot fall into the buffer window of each other. In this case, each request will basically, each user will basically request the content from the server. Okay. After this threshold, when the request rate continues to grow, the inter-arrival time of the neighboring requests will getting smaller and smaller. When they're getting smaller and smaller, they fall into each other's buffer window. They can reuse each other's content. When they do the reusing content, they will offload the server. The server load will be decreased. So what is the threshold to achieve the to achieve the highest server load here? This is the time when the average request into arrival time equals to the time length of the buffer window. Okay. Before that, the inter-arrival time is bigger than the window. So in this case, you cannot reuse the content. After that, the inter-arrival time is smaller than the time window. The buffer window. In this case, you can reuse the content. So I consider this a very nice feature because in overlay, it means that in overlay multicast, when the capacity of the server can be actually bounded to serve any request rate. So this is the analysis part. And then I do the simulation part, and I see that the curves basically match, which actually confirms our analysis. Yes?
Right and the left?
Right and left. This is the sequential access mode, and this is the random access mode. Yes.
What do you assume as the random access mode?
Random access mode, what do I assume there? This is the length of the movie. Okay. As here, you see, as is unique to to the in the random access mode. So as is the average playback time. So what do I mean by average playback time? So each time, in the case of random access mode, each time I do a playback, I won't play back the whole movie. I just play back the one portion of it. The average length of the average portion that I play is this, is as here.
So you pick a random starting point and play for S?
Average of S. Average. So when this is the difference here. Okay. When I do the analysis, I do what exactly you have proposed. I choose a random point and I play back for S. Okay. The playback is actually fixed. When I do the experiment, when I do the analysis, I do this. I pick a random point. Also, the length of the playback is also random, but the average playback length is S.
And on the IP multicast, what's the model for that?
The model actually is the same. The
I mean for the delivery.
For the delivery, okay. Let me see. This is quite complicated. Let me try to. Yes, we can keep this offline. Probably will consume maybe 15 minutes to talk about the delivery model of IP model. One thing I have to say is that the delivery model of IP model is quite sophisticated, actually quite successful in the context of IP multicast domain. You see that this curve increases, of course, monotonically increases, but actually scales very well. This is the logarithm curve. This is the square root curve. That's why the curve in this case goes up so much, way more quickly than the curve here. But that's the best that they can achieve. Very beautiful theoretical model in the context of IP multicast.
Another question is if W equals T, then the whole thing collapses to 0, right?
If W equals let me see. If W equals to T,
you give people, everybody can buffer the whole movie, then the server doesn't have anybody, right?
the server will only have let me see. The server will just need to serve the first guy, and that's it. Right. Yes. Yeah. Okay. While we're on the subject, we can talk a little bit more details about this graph. So let's see. Okay, this is different lines. When I say the buffer equal, the length of the buffer with regard to how the portion of the whole movie. This is the case when the buffer is only 5% of the whole movie. This is the case when the buffer length is 10% of the movie. This is the 20% of the movie. So you see that is actually I choose to increase the length of the buffer. I let the length of the buffer to grow exponentially. Okay, and you see that with regard to the peak server load. The peak server load actually drops linearly. So anyway, so the key point I want to say here is that you don't have to make buffer very big. Your buffer only needs to be small or medium size regarding the length of the whole movie. So with relatively small overhead at the storage, relatively smaller storage overhead, you can achieve pretty much a very big performance gain in terms of server load. That's all I want to say. Yes.
On the MSG simulation and what are the new things you see in the MSG simulation, and also how large is the scale of the simulation?
I don't see too many new things here. Okay. The only thing I see, in addition to the closed form analysis here, is that for the random access mode, I choose to for the analysis part, I have to make the playback portion, the length of the playback fixed. Otherwise, I cannot derive a closed form analysis result. So when I do the random access, when I do the simulation part, I don't have I have this freedom to choose different ways, and I see that the result is always stick to it. The other thing is this: when I perform the analytical study, the arrival pattern, the user arrival pattern follows the Poisson arrival. Again, because I want to have a closed form result. So when I do this, when I do the simulation study, I can try all kinds of, user arrival patterns. The picture you see here is still follows the Poisson arrival patterns. We have more results. If you're interested, we can show you. So these are the freedom I have when I do the experimental validation. So your second question is the scale, right. Not too much. NS2, that's the biggest problem of NS2. So for NS2, my personal experience that you can only have up to 400 receivers. When you try any scales after that, the system basically freezes. So what I do here is just, I have limited number of nodes shooting out requests, keep shooting out requests, as if these nodes will have multiple requests at the same time. That's how I achieve the result here. Now we can build simpler simulation tools to accommodate bigger scale. We can certainly do that. Okay. Networking cost. Now I talked about server load. Now I talked about the network bandwidth consumption. So I use the same methodology here. Okay. So a key intuition here in this part of the study is that in multicast, you want to try to group as many number of receivers into one tree as possible. And here's why. Now look at this piece. Look at this picture. If we have only one source and one receiver, so what is the average overhead to deliver the content from source to receiver? 1, 2, 3, 3 hops. 3 hops for one receiver. Now let's say we have two receivers here, the red and the yellow. Now how many times the packet have to be delivered to reach both these guys? 1, 2, 3, 4, 5. 5 over 2, 2.5 for an average receiver. Okay. If you have 3 receivers, the packet will be delivered 7 times. 7 over 3 is smaller than 2.5. So the key thing here is that the key intuition here is that the more number of receivers you can group into one tree, the smaller the average overhead, the average delivery overhead to reach a receiver. So now, what we want to see here is this. So overlay multicast is not, in terms of the network transportation overhead, overlay multicast is not as good as IP multicast because of the topological inefficiency problem, because of the packet replication problem. But overlay multicast, as we see here in the server load study, overlay multicast is able to group more receivers into one tree than the IP multicast. Now, what we want to see here is to see which factor wins over which. Okay, so this is a picture. This is the analysis. Now, a very hard thing in analyzing the networking cost is that if you want to derive a closed form analysis result, you have to stick to a particular topology, to a particular physical networking topology. Okay, this is one of the topology, a tree topology that we chose, and this is the result. So, you see here that as request rate increases, okay, the average load, the average overhead to deliver content to one receiver drops, both in case of IP multicast and overlay multicast. The starting point for IP multicast is lower than overlay multicast because IP multicast in general is more efficient than overlay multicast. But overlay multicast drops faster than IP multicast when the request rate grows because of the second factor that I mentioned, because overlay multicast is able to group more receivers into one tree than IP multicast does. So if the red line drops faster than the blue line, and then sooner or later the red line is going to catch up with the blue line, and then starting from here, overlay multicast beats IP multicast.
Groups them into a tree. It's all a tree.
I see your point. So this, you see that these 3 receivers are grouped into one tree, okay, to serve, because they share the content, they share the same particular piece of content here. because you see here for the sequential access mode, you're absolutely right. They're just one tree. You know, they always join one tree. But for the random access mode, actually, different receivers want the same different pieces of content at different time. In this case, you have to build multiple trees. You know, for all the receivers wanting different parts of the movement. Again, we can we can discuss this offline about how that, you know.
I think the point he is trying to make is for IP multicast, you are trying to basically one tree of IP multicast, all the receivers which are requesting content at the same time. Basically, all the receivers which are starting to build a movie at almost the same time form one multicast tree. And you do multicast again, let's say every 10 seconds. With
Let's
the interval being a narrow buffer. And for the overlay multicast, you have one tree related to the buffer length for the basically node. And then you have a buffer length, basically narrow buffer length, maybe larger. You are basically having more trees.
What's it? I mean, a tree. Are you saying a tree is for each branch out of the each child of the root? Is one tree?
For the IP multicast, each tree is basically all the nodes which is able to receive the content all from the same time. Right on the different set. And for the overlay multicast, each tree is basically those nodes that can reuse other people's content.
let's further discuss this offline. We have lots of things to talk about. Okay. Now this is the first piece of work, and so the key thing I learned here is that content reusing can enable by the end-host caching space can greatly help. Okay, to overcome the inefficiency of the topological inefficiency. So the result shows that actually overlay multicast can beat IP multicast. Okay. Second piece of work. So in this piece of work, I talk about how to maximize the throughput in overlay multicast. Now, idea is still quite straightforward. You split your content into multiple pieces, okay? Then you distribute them over different trees, okay? So you explore the world diversity in overlay network. Now the question is, how do you know? How do you know what is the maximum throughput? Given a certain multicast session with one source and so many number of receivers, how do you, on top of a physical network, how do you know that? How do you know what is the maximum throughput achievable in this case, in this multicast session? Second thing is, how do you know how to achieve it? How do you know, how many number of trees are needed and how to build these trees to achieve this throughput? Now, this is how we formulate the problem in the linear programming setting. The primal formulation of the problem goes as following. So you have so many number of trees and you want to maximize their throughput. So F1, F2, F3 here refers to the rate of each tree. So notice that each tree here, so each tree is a single rate tree, which means that each edge here of the tree have the same rate. Now you want to maximize the summary of the whole. You want to make the summary of the tree rates, the rates of all these trees, subject to the physical link capacity. Now, the deal of this problem says the following: you want to assign a weight to each physical link here, okay? And what you want to minimize is the weighted sum of the capacity of all the links here. Weighted is the capacity of the link weighted by the link weight that you give to each physical link here. And the constraint here is that the weight of the minimum overlay, the weight of any overlay tree, okay, the weight of any overlay tree in this physical network has to be bigger than or equal to 1. So this is the dual formulation. So the primal wants to maximize something. The dual wants to minimize something. And the optimal value of these two formulations meet in the middle, which means that the maximum value of the primal problem is equal to the minimum, the minimum value in the dual problem. I try to maximize. You have a source.
What
You
sessions are we talking about? Are we now talking about it?
Yes, go ahead.
What's a session?
Our sections are all done the same thing. Basically, for the network,
You have a source here. You have these receivers. All these nodes form a session. Okay. A tree in this session is a tree that reaches all the nodes here. Okay.
Yeah. And how many do you have?
Lots of them. And
Okay, so we have a lot of
Okay.
let me.
Okay, so you just want to maximize the number of spanning trees you're packing. Yeah. Okay, fine.
Okay, let's go ahead. So that's the basic. So how do you build the algorithm? So this is how the algorithm goes. So initially, you assign a weight to all the physical links here. The weight is normalized by the capacity of the link, of each physical link. Then, based on the initial weight, you find yourself in minimum overlay tree. Okay, based on the weight here. Okay, it's assigned for a minimum overlay tree. Then you route a certain amount of traffic, on top of this tree. Then you update the weight of these physical links based on the traffic increment. Okay, this is the function you want to follow. So basically, you scale up your weight by this form here. Now, after this step is done, you get yourself a new set of weight for the physical links. Okay, then, all right. Then based on the new sets of physical link weight here, you find yourself a new tree, new minimum overlay tree based on the new weight here. When you find a new tree, you again route the traffic and update the weight. So the circle goes on until certain stop condition is met.
Then how do you recover the primal?
How do I what?
How do you recover the primal solution?
So each time a circle is finished, a loop is finished here, I get myself a tree. Okay.
But that tree may not.
That tree is actually part of the solution.
That tree may not satisfy all the constraints.
What do you mean by?
Capacity constraints.
Okay. That's right. That's one of the details of the algorithm. Yes, that tree may not satisfy the capacity constraint. Okay. So at the end of your algorithm, when you are done, you have to scale down. Okay. You have to keep track of the how much traffic is loaded on each of the physical link here. Okay. When I run the algorithm, I'll allow the load on the link to exceed its capacity. Okay. That's fine. So when I'm done, I want to scale down it. I want to scale it down. For instance, if the capacity of the link is 1, okay, so when the algorithm is done, the load on this link is like say 1.5. Of course, this solution doesn't work because it exceeds the capacity. So what do I do? I would just scale down the traffic load over all the links by the factor of 1.5.
No, that doesn't solve the problem because the optimal solution might use more than one tree. Right?
Yes, yes.
Here, if you stack, for a given weight, you only find one tree.
Yes.
You find one tree. How do you reconcile it? The optimal solution.
The algorithm will go along many cycles. Each cycle, I find myself a tree. Okay.
Yeah, so
All these trees combined together, give me the solution to
So
the.
you have to remember that.
Yes, I have to remember exactly. So okay, this algorithm is not practical in the real deployment, as I will explain later. So, what the usage of the algorithm will be revealed in the next slide. Okay. Let me finish with the intuition here. Intuition is this: the weight of your link represents the cost of your capacity of the capacity of your link. So the intuition is this: the more your link is loaded with the traffic, the more expensive your link will become, because the weight is bigger. So the effort to find the minimum weight spanning tree is actually equal to finding the cheapest route to route your traffic. The cheapest route actually is the most lightly loaded route. So the weight here is a very good indicator to indicate the current traffic condition, which also reflect the price of your physical link based on the current resource usage. So that's the intuition of the algorithm. Now, another thing I want to clarify: I didn't invent this algorithm. This is the typical solution, very classical algorithm, widely used in the domain of multi-commodity flow problem, multi-commodity flow problem, also in the linear programming. So what I did is to apply this technique into the domain of overlay network, and I find that it works pretty well. I actually solved the problem. Now, so what I learned from this? We learned that actually maximizing throughput in overlay multicast is a solvable problem. It's solvable in polynomial time. This is radically different to the case of IP multicast. IP multicast, maximizing throughput in IP multicast is an NP-hard problem. But we find out that this problem is actually solvable in the domain, in the context of overlay multicast. Now, the shortcomings of the algorithm. First, it is a centralized algorithm. It cannot be distributed. Second, the algorithm will create lots of trees just to achieve this optimal rate. So one experiment I did is that I tried a multicast session with 7 receivers, and the result I got 397 trees just to achieve this optimal rate. So this algorithm is absolutely not practical. Third, the algorithm doesn't incorporate the node dynamic problem. So let's say if a node join or leave the session, so anytime the membership changes, I have to tear down all these existing trees and build a solution from ground up just to achieve the optimal rate. So the algorithm I just introduced is not practical at all. But why do I still want to research on this? The reason is this. This algorithm can tell me what is the optimal rate. So that means the algorithm can serve as a very good benchmark to evaluate the practical algorithms. Okay. For instance, let's say you develop a practical algorithm which can build limited number of trees, which can also accommodate the node dynamics. But what is using my algorithm as a benchmark? I can tell you, how close your algorithm, performs close to the ceiling, to the optimal rate.
Maybe just compute the main cut. It's more complex. Yeah, main cut. Your main cut average.
Let's say min cut. One source, one destination, min cut, no problem at all. Not broadcast.
Yeah.
This is multicast.
Yeah,
multicast.
one source each. No, if this is multicast, this broadcast as an overlay.
Yeah,
It's actually as an overlay. It's a broadcast.
I see. So, okay, because it's spanning tree problem, right?
Yeah.
Yes, right. In the talking about spanning, you can consider it as a broadcasting problem in the overlay domain.
Saying that the optimal throughput is actually the min cut in the source of the destination. Minimum over min cut from the source of each destination.
But can you solve the problem in case of there are multiple sessions? If there are multiple sessions coexist in the same physical network.
No.
This one does. This one does. So what I propose here is, the algorithm, the version to handle the single session problem. There's another variation of the problem called maximum concurrent flow, which can compute the throughput, optimal throughput, achievable optimal throughput if there are multiple sessions. That's one variation. It's called maximum flow. If I want to summarize, just the throughput of all of them. Another version is this. You have multiple sessions. Each session has a demand. Let's say we have 2 sessions. Session A says, I want to demand 1. Session 2 says, I want to demand 1.5. So what the solution will give to you is optimal is the proportional fairness. So I will give you the throughput maybe higher than the demand or lower the demand, but the proportion is the same. That's what the algorithm does. Okie dokie. So looking back, I have done I presented two pieces of work. One to deal with the on-demand challenge. The other one deal with the throughput challenge. Now it's the time to combine the things I've learned, the solutions I have developed into one practical solution here to address both of them. Now, if I try to develop a solution to address both challenges, the optimality will be lost. Okay, but excuse me. Good thing is that I have a benchmark algorithm which can tell me, how good, how close my solution is going to perform with regard to the optimal throughput that is achievable. So which leads to the final piece of the work, which talks about the dynamic high bandwidth overlay multicast. So we talk about these two challenges here. The new challenges are these. First, you cannot afford to build hundreds of trees for just one session. You want to limit the number of trees that you want to build. When you do that, when you try to limit the number of trees that one session can afford, you basically impose another constraint to the problem. That makes your problem NP hard. But that's fine. We can develop an approximate solution to that. The final challenge is the overlay comes from the overlay network. So what happens is this. So far, in the algorithm that I've proposed in the second piece of my work, I assume that the overlay session has the entire knowledge of the physical network. So I know the knowledge, know the topology of the physical network. I also know the capacity of each physical edge. But that, in reality, I cannot have such a clear picture, over the entire physical network. Instead, I only have partial knowledge over the physical network. So now the question is, if you only have partial knowledge, how would you accommodate this situation here? How does that reflect it in your algorithm? Again, now this picture looks familiar to you. Okay, I'll draw the overlay graph again. Your purpose is to find a tree on top of this graph. The only thing changes here is the weight of the edge. Now, initially, the weight of the edge in the overlay graph is fixed. Okay, it's only the distance between two nodes. Now, I want the edge weight to reflect the current traffic condition. So now, in this picture, the weight of the overlay edge will be updated constantly whenever the traffic load on top of this edge is changed. Okay, but still, I want to find the minimum spanning tree basically on top of the overlay graph. I want to talk about the basic operations. I want to talk about extensions that I make to the basic algorithm here. Now, let me first talk about how do I define the link weight function here. The way I define the weight of the link actually inherits from the baseline algorithm that I have developed in the second piece of work. Initially, when there's no traffic on the link, this is the initial form of the weight. So it's basically a constant value normalized by the link capacity. So the intuition here is that if your link has more capacity, your link will be cheaper. Okay, the weight will be smaller. Now, each time a certain traffic is loaded, to this link, I will scale up the factor. I will scale up the weight by this factor here. The rho here is the step size. This is actually the portion that your traffic occupies on top of this link. Step size, rho is the step size which basically reflects the sensitivity of your algorithm to the traffic load. If the load is too big, then probably your link weight function will overreact to the to the additional traffic loaded to your link. If your road is too small, probably your algorithm will not be agile enough to find alternative routes just to avoid congestion, basically. So that's the basic definition of the link weight. Now, this is the definition of weight of each physical link. Okay. The overlay weight is the weight of the overlay edge will be the aggregate weight of all the physical links on route. All right. So that's how we define the weight. Again, this picture looks familiar to you. When a node joins, I will just follow the same procedure here. The only difference here is this. When I'm done here, I will update the link weight based on the function here. Okay. Now that's the joining part. Leaving part, still the same. When I'm leaving, I tell my children to reattach themselves to the tree. And whenever they do that, okay, there are two parts. When I'm leaving, there are certain parts of the traffic which is offloaded from the link. I will have to, remove that certain part from the link weight update function. And when the children reattach themselves to the tree, they also want to update the corresponding link weight, okay, to reflect the additional load. That's the basic algorithm. Now, here comes the point about the topological awareness issue. So what happened here is that, what if you don't have the entire knowledge of the physical network? What if you don't know what the underlying topology is, and you don't know the capacity of each of the physical links? So this is the modified function that I propose. I assume that I have some end-to-end measurement tools available to me to tell me the hop count, which means how many physical links I have to go through, from the source to the destination. That's the first thing I want to know. I can get this knowledge from various tools such as traceroute. Second thing is that I want to know the available bandwidth for myself from one point to the other, which means that I want to know the bottleneck bandwidth, along this route. And then we have quite a few bandwidth estimation tools to help me get this knowledge. So these are the two things I want to know. Now, how do I update? Yes, how do I update the function here? The function will be updated, updated as follows. So the initial weight will become the hop count, normalized by the bottleneck capacity of this overlay edge. And this part is still similar. So every time a new traffic is loaded on this overlay edge, the weight of this entire overlay edge will be scaled up by this factor here. So it's a flow rate normalized by the bottleneck capacity of this overlay edge. That's how I update. That's how I change the weight function for the overlay edge, and the rest of the algorithm stay unchanged. Rearrangement means the following. So as there are nodes, constantly joining and leaving the session, it can happen that your tree becomes suboptimal. So if your tree becomes suboptimal, I will allow you to change to basically, reattach yourself to another node in the tree. Or even though your parent is still alive, the parent is still alive, I can allow myself to attach myself to a better node. So what is the threshold? So there's a threshold, which is the triggering, let's say, so threshold here is actually the ratio of the weight of the overlay edge weight of my, for myself to my current parent, to the overlay edge weight for myself to another node, to another node in a multicast. If it turns out that the weights of these two weights are too different from each other, let's say the threshold exceeds 1.5, a rearrangement will be triggered. Okay. Of course, when I do that, when I reattach myself to the new node, I want to update the link weight accordingly. How about multiple trees? Well, the algorithm is still quite straightforward. In case of multiple trees, you just enter the loop here, and each time you just, find yourself the minimum spanning tree. Find yourself the closest neighbor as your parent, and you update the link weight accordingly. Then you return to the loop and find yourself another closest neighbor based on the new updated link weight. So that's how you find. That's how you extend your algorithm to the case of multiple trees. So these are some of the theoretical results I have derived in this piece of work. The way I measure the performance of my algorithm is that I want to measure the ratio between the throughput achieved by this algorithm, by the realistic dynamic algorithm, and the optimal throughput achieved by the primary algorithm that I introduced in the second piece of work. Okay? This is called competitive ratio. So obviously the throughput is definitely smaller than the throughput of the primary algorithm, but what I'm showing here is that this ratio is actually bounded by a constant factor. Now, these are the different scenarios. If the multicast only allows joining, which means that the node will keep joining the multicast, but when it does, when it joins, they will stay there. They will not quit. In this scenario, the approximation bound is this. So L here is the number of physical links in the entire network. If I allow the node to join and leave anytime they want, okay, and this is the approximation bound, which is bigger. Okay. If I allow the node to join and leave, also I allow the node to rearrange themselves, to reattach themselves to the tree, occasionally. One time, occasionally to a better, to a node with better link weight, the approximation bound will return to the bound of the to the situation of joining only. Okay. This is the best bound we have achieved so far. Now, the last thing I want to say is that all these results will hold when we change the link weight function from the physical link-based, physical-based weight update function to the overlay-based link weight update function. So when the weight update function is changed, actually the approximation bounds don't change. So this might come a little bit surprise to you, because when we switch to the overlay-based link weight update function, we actually lose lots of knowledge. We only have the partial knowledge of the physical network. How come? In this case, we still get the same bound as the case of the physical link based weight update function, which means that the function has the entire knowledge of the physical network. So one thing I have to say is that this bound, the bound here, is actually pretty loose. Okay. This is the bound here it's actually very big. But so far, this is the best achievable bound, even in the case of unicast routing. And another thing I want to say is that in the experimental part, we find out that the comparative ratio of our solution actually is way better than the bound, than what is specified here, than the bound. So actually, all these bounds are quite loose. So can we further improve these bounds? We don't know. This is the best we can do so far. Yes.
So when you compute the optimal throughput of primary dual aggregate,
yes.
what is the capacity constraint for that?
What is the capacity constraint of?
Set up the capacity constraint.
You mean in the experiment?
Yeah, because you said in practice you don't get the capacity.
So your question is?
When you're comparing the practice with the dynamic aggregate with theoretical primary dual aggregate.
Yes.
For the primary dual aggregate, what do you use to characterize the bandwidth constraint?
So what do I use to characterize bandwidth constraint? Okay, I'm not sure if this is the answer you want. So basically, the primary algorithm functions like a black box. So what do I mean by that? You give me a physical network, and you tell me, you give me the topology of the network, and you tell me what is the capacity of each link in this network. What I mean is, you give me a specific instance of this network, and you tell me what is the session, multicast session on top of this physical network. What is the source, where is the source located, and how many receivers you have. You give me all this input. My algorithm will run and tell me what is the result, what is the best achievable throughput in this particular instance.
Okay, so you basically have link capacity constraints on the underlying.
That's correct. That's correct. Okay. This is theoretical results. Okay. Performance evaluation. Now, this is the basic setup here. I run 2 overlay sessions. Okay. These are the node will join and leave at any time they want. I just create a random sequence here. Okay. This is, so the blue line here shows you the optimal achievable throughput as time goes by. As time goes by, different nodes will join or leave the session. So each time instance here actually represents a different multicast group. Okay. And each time a group membership is updated, I will run the optimal algorithm, the primary algorithm from scratch, just to get the optimal throughput. So the black line here you see is really the ceiling. Okay. is the best achievable throughput. These are the throughput achieved by the dynamic algorithm. By the algorithm, by the algorithm that only returns a single tree, okay? And this is the throughput achieved by the single tree, by the single tree solution. Now, so the observation I draw here is the following. The single tree solution can actually approximate half of the optimal rate. So, second thing is that in order to achieve the seeding here, the best achievable rate here, it will cost you a great number of trees, as shown here. Okay. These are the number of trees needed to achieve the optimal rate. As you can see that the number of trees can actually go through hundreds of thousands. And this is not surprising, actually, because according to the Cayley's theorem, so Cayley's theorem states that the number of different trees in the multicast session equals to this. N here is the number of receivers. So it's exponential function. So actually, the percentage of all these possible trees are only occupy a very small portion of the total number of possible trees. Okay, so this is not surprising. And the whole experiment here shows that with a single tree, you can actually approximate half of the optimal rate ever achievable with the multi-tree compared to the multi-tree solution. How about multiple trees? Again, you see here is the black line here are the seeding, okay, the best achievable, the optimal achievable rate. This is the rate of one tree. This is the rate of 2 trees, 4 trees, 8 trees, 16 trees. So what we see here is that as you increase the number of trees, okay, every time you just double the number of trees, the improvement space is actually limited because as we have seen here, single tree already give you half of the rate. The rest of the improvement space is the other half. Okay. And you see a very clear diminishing return when you further improve the number of trees. And the second thing we learn here is that this is comparison of the physical link-based weight update function and overlay link-based update function. So what we see here is that just in the context of this experiment, the the algorithm returns comparable performance. The two algorithms return.
What's the underlying
topology? I use a Waxman model, which is basically a random graph model. And the scale of the network is not so big. The reason is I want to compare the performance of my algorithm to the optimal algorithm. And this optimal algorithm will just kill me if I increase the scale of the network, because the optimal algorithm will run very big amount of time just to see the number of trees the algorithm has generated. So the results, the conclusion I have drawn is limited within the context of my experiment. I don't intend to generalize my conclusion here, because just to figuring out what is the optimal throughput it takes too much overhead unless I have a very powerful computer. Effect of rearrangement. So what we see here is that if you set the rearrangement threshold too low, you only have limited performance improvement. Okay, so which means that rearrangement doesn't improve so much, doesn't help so much in this case. And also we see that with the overlay-based link weight update function, the algorithm returns comparable performance. Okay, number of rearrangements, but so we don't get too much performance improvement when we introduce the rearrangement functions, but we pay considerably because for this new functionality, because as we lift the threshold linearly, the number of rearrangements, as we decrease the threshold linearly, the number of rearrangements actually will increase exponentially, which means that rearrangement maybe doesn't work so much. Again, in the context of our experiment. So, in conclusion, I have presented three pieces of my work in the context of overlay multicast. So what I did here is that I first focused on individual challenges each of these individual challenges. Then I combine the solutions I have developed in these two pieces of work to come out with the third one. So that's the conclusion, and these are the new things we have learned, which is in the case of layer streaming. Okay, so layer streaming means that if you have heterogeneous receivers, okay, and these receivers want different quality of the stream, so you can address this problem using layering approach, which means that you cut your original stream into layers, and you ask the different receivers to receive different subsets of layers, okay, to basically get different quality of the stream. So the thing we find out is that in the context of layer streaming, the multi-commodity flow formulation still applies. We are still working on this to get some more results out, to get some more results, in this experimental context. So, if you're interested, please stay tuned to the development of our research. So, that's almost the end of my talk. So, I have summarized the research I have done in my doctoral years, and some of the final piece of the work is actually is my research after I joined the Vanderbilt. For my future research, one thing I'm particularly interested is this. So in the traditional networking research, there's one assumption we hold is called flow conservation. So flow conservation means this. If you're a router in the middle of the network, so the amount of traffic entered this node equals to the amount of traffic exiting this node. Okay, so the conservation always applies. Multicasting is one exception, but you can easily count, the additional number of copies replicated within the network. So the key point here is that in the traditional, networking model, the data is treated as meaningless bits. So if you are the relaying node, you don't really read into the semantics of data, what this data represents, what they denote, what they are representing. So in network data processing means that we can employ additional functionalities into the relaying nodes, such as compression, composition of the content. So all the functionalities other than routing and replication. So when we do that, how do we formulate the problem actually? How do we run the problem formulation? What is the thing that we try to maximize or minimize? What is the constraint that we're dealing with? So all these are open questions, and I'm personally very interested with this line of the research. And also, I'm interested with the management of intelligent autonomous systems. I have done some research about digital rights management when I did intern here, and also I'm interested to apply this technique into other domains of networking, such as sensor network. So I think that's the end of my talk, and I keep updating my latest research development in my personal webpage. So I would love to welcome any questions. So, thank you.